Cheat sheet for Abg interpretation. Our body keeps the pH around 7.4 using the buffer system. Equation: if we see water plus carbon dioxide gives carbonic acid, which again can be dissociated into H++ CO3-. Here, carbon dioxide's normal range is 14 millimeters of mercury, which determines the respiratory system, and it is a rapid compensation process which takes up to 12 to 24 hours. Bicarbonate is determined by the kidneys. It is a slow compensation process, which takes 5 to 6 days. The H+ determines the ratio of bicarbonate to carbon dioxide. Now looking at the Henderson-Hasselbalch equation, where pH is the negative log of H+ ion concentration, which is equal to 24 into carbon dioxide divided by bicarbonate. Interpretation. Step 1. Look at the pH. Acid-base status. Normal range is 7.35 to 7.45. If it is less than 7.35, it is acidemia, buildup of acid in the blood. If it is more than 7.45, it is alkalemia, build of alkali in the blood. Step 2. Look at carbon dioxide, the respiratory component. Normal range is 35 to 45. If it is less than 35, it is respiratory alkalosis. If it is more than 45, it is respiratory acidosis. Step 3. Look at the bicarbonate, metabolic component. Normal range is 22 to 26. If it is less than 22, it is metabolic acidosis, and if more than 26, it is metabolic alkalosis. Step 4. Determine the primary disorder, whether it is the respiratory component or the metabolic component. If the pH and the carbon dioxide move in the opposite direction, then it is the respiratory component. But if the pH and the carbon dioxide move in the same direction, then it is metabolic component. Step 5. If metabolic acidosis is there, then we have to identify the gap. Formula to calculate the anionic gap is sodium minus chloride minus bicarbonate. Let us take the cutoff as 10. If the anion gap is more than 10, it is high anion gap metabolic acidosis. If it is less than 10, it is normal anion gap metabolic acidosis. Step 6. To find out the delta ratio if there is more than one acid-base disturbance. Delta ratio is the calculated anion gap minus expected anion gap, which is 12 divided by normal bicarbonate, which is 23 minus measured bicarbonate. If delta gap is more than 2, it is high anion gap metabolic acidosis plus metabolic alkalosis. If the delta gap is 1 to 2, it is pure high anion gap metabolic acidosis. If the delta gap is less than 1, it is high anion gap metabolic acidosis plus normal anion gap metabolic acidosis. Step 7. Check for compensatory mechanism, 1 metabolic acidosis. Winter's formula, which is 1.5 multiplied by bicarbonate plus 8 plus or minus 2. This formula is used to calculate the expected PaCO2 compensation. If measured PaCO2 is lower than the expected, then respiratory alkalosis is also present. Second, metabolic alkalosis. Rise in PaCO2 by 0.5 to 0.7 for each 1 milliequivalent of bicarbonate is seen. 3. Acute respiratory acidosis. There is 1 milliequivalent rise in bicarbonate for every 10 millimeters of mercury rise in partial pressure of carbon dioxide. 4. Chronic respiratory acidosis. There is 3.5 milliequivalent rise in bicarbonate for every 10 millimeters of mercury rise in partial pressure of carbon dioxide. 5. Acute respiratory alkalosis. There is 2 milliequivalents decrease in bicarbonate for every 10 millimeters of mercury decrease in partial pressure of carbon dioxide. 6. Chronic respiratory alkalosis. There is 5 milliequivalents decrease in bicarbonate for every 10 millimeters of mercury decrease in partial pressure of carbon dioxide.